All right, let's see. So we have a few people have started the hash table. So swing, let me know as we get through tonight. If you have any questions on it? Okay. Let me see where we are with our collision resolution. We talked about chaining already. So we got chaining. Chaining and bucketing. All right, good. Did I make the test word practice available? I thought it was available. So let me see what I did there. I forgot to hit the publish button. Okay, sorry. Yep. Let me make that available. I thought it was already was. Let me check 5 practice. Get that there while I'm at it. Okay, yeah, we'll swing by that one later tonight. Okay, locality reference. This is a pattern of resource usage that can occur temporally, spatially, or sequentially based on the common resource usage. Various techniques have been built to leverage those patterns. Basic idea is to improve resource access. All right, so temporal locality is based on the timing of how recently things have been used. All right, the common pattern being that something that was recently used is more likely to be used again in the near future. And something that hasn't been used for a while. One second. Knocking things down over here. Okay. All right, so for example, so we have some code section A as variable A equals 10 or something like that, B equals 25, and somewhere down further along, we have some sort of loop. And an array of values. Then we loop on that set of values. Whatever some count is. And we get the sum out of the array. All right, so we have bunch of variables in memory. Variables in scope. We have var A, var B, sum, array, and I. All right, so depending on how big the system is, how much layer of caching they might have going on in there, when the program runs, A and B are relevant, and this code block is possibly making use of A and B, add them together, subtract them, multiply them, divide them, whatever happened to be the case, and it spat them out, and then code kept running on into other sections of code, but these variables still exist in memory because it's just much too large function going on here. When we get down into this part of the code, we start working with sum, array, and I to do this workload, whatever it is. These three variables are more pertinent than A and B are, even though they're all still defined in the same scope. So as we use sum, array, and I recently and more frequently, what the system can do is keep these areas of memory closer to the processor. All right, so let's do a slight segue here. Go look at, let's see, where are my components? There we are. Some random processor. Get down into the specs. If the screen stop pops around on me, where the specs go, there. All right, so the processor is going to have cache on it. The idea of caching, which is a double-edged sword, is to improve performance of the system. All right, so we'll have our CPU here. And then we have various caches. And there's probably an L1 cache as well, but just work on what we have here. And we have two areas of memory, right? We've got RAM, and then we'll put our disk system to the side over here. and disk. And depending on how massive your application is, the data might be in any of these locations, right? Initially, your application is on disk, gets loaded up, loaded into the RAM, and then our instructions get fed into the CPU and all that good stuff. And then variables that exist in RAM can also be pushed down into the lower levels of cache, right? Before even getting into the CPU and the registers and added together, all the fun stuff. Don't worry too much about the computer architecture here. That's outside the scope of this course. We're simply going to be very high level talk about it because locality reference is driving the design of the CPU and why these caches exist in the first place. Right, so yes, the L cache is much faster and consequently much more expensive, which is why it's much smaller. Right, our RAM, which is probably, what, say 32 gigabytes. In RAM, we have our various variables, where there's var A, var B, I, sum, array, right? All on a stack frame somewhere that's inside the RAM when we call this method function. It's possible A and B may have made it into the L2 or L3 crash, depending on how much activity there was going on in that chunk of code that is just represented by an ellipse. As we get to the array part, especially if the count is quite high, that's right, I forgot to mention count. We're going to be reading I often. We're going to be mutating I often. We're going to be reading some often and mutating it often. We're going to be reading array often, but not mutating it. And the count is also going to be fixed during that life cycle. So what's going to happen is these variables, as they get more used, they're going to work their way into the cache, and depending on how much things are going to be used, they'll work their way up. Right? And the reason what you were asking is the L2 cache is substantially faster than L3 cache, and the L3 cache is substantially faster than the RAM, and the RAM is substantially faster than the disk in case any virtual memory is going on here. So as applications idle out, if there's a lot of RAM pressure, the operating system can unload parts or entire applications from RAM and then stick them on disk. And if the application needs to do something again later, it'll bring it back from disk into RAM and then again back into the CPU. Right? We have our buses for the communication between the various components, but the memory that lives on the CPU itself is part of that circuit. The actual physical distance the CPU has to go to get to these caches is shorter. The quality of L2 cache is much higher. I don't remember the magnitudes. L2. Let's see if I can find something quickly. There's the cores, all fun stuff. That was not helpful. Let's see. Now, one cache is usually in kilobytes. Last I looked. I wonder if there's a way I can just select all this and move it out of the way. So there is. Good enough. Get my mouse back. There we go. Size and speed is not giving me our proportions. But this does look like it's a good read. I will link there. But yes, the speed of, basically we sacrifice space for speed, much like we do with other data structures. So we give it more space and give it more speed. Here, we're giving more speed, but we have less space that we can actually store things because of how off. See, we may have lost everybody. Okay, that's fine. I've got the image over here anyways, if I can click. All right, L1 cache, which they're not even bothering to advertise, is probably 768 kilobytes. That's the last time I remember seeing it advertised in Newegg. And each core probably has its own L1, L2, and L3 are possibly shared. Depends on the chip design. You see in this particular one, they've got a box up where the core has got the L1, L2. And I'm paying closer attention, L3 is shared across. And of course, you got the GPU, which is its own separate discussion, especially if you're mining. So, yeah, so the fastest and the tiniest are right here in the processor and still infinitesimal compared to the RAM sticks that you've got in there in terms of capability, right? Because RAM is going to be measured in gigabytes, L2 and L3 measured in megabytes, and L1's probably measured in kilobytes. Right, so if you have we had this array and it was sized as 1 million elements, right? 1 million element array at 4 bytes per array, probably not going to have all of it inside our L1, L2, or L3 cache at all. We might have a subsection of it, which is in the sequential part, which we'll get to in a minute here. But the idea is, because I keep using things like count, which isn't changing, and the array reference, which isn't changing, those two values are good to have quick at hand. Because if we have them nice and easy to reach, it's kind of like the same idea with the keyboard, right? The letters that you use more often, if you don't have to do any travel time, you can get to those keys faster. So as the application is doing its running, just look temporal locality reference. If I recently used something, I'm more likely to use it. So what's going to happen in the processor, it's going to maintain these caches, and it's going to see how often did I hit it. It can do other things as well, like how many times have I hit it. If I've hit it frequently, then the odds are higher that I'm going to hit it again in the near future, right? Because the variable I've used 3 times is a variable I used 3 million times. Well, what are the odds that I'm going to use the variable that I used 3 times again in the near future versus the one I've already used 3 million times in recent history? And the other trick is how you start aging these things out, because this space is very, very finite, very, very small relative to the size of RAM and memory that we want to make use of. New things want to come in, so that means old things have to go out type thing. And then one tends to be an age-based eviction pattern. Right, so something that's been around for a long time but hasn't been used, it's a good candidate for getting rid of. Something's been around for a long time but it's used often, not a good candidate. So the CPU architecture is going to be handling all that good stuff. Let's see. So the next part is space. Space is, and sequential. Sequential is also space-based. It's just a subsection of spatial. So our space-based locality of reference. Things that are near, clear those drawings. Another resource being used or requested is more likely to be used than a resource that is further away. All right, so to an example, if we have multiple methods on the stack, all the local variables in the current stack frame are more likely to be used than variables in the other stack frames. Right, and this one's kind of a ridiculous environment because, right, we're only using the top stack frame until that stack frame goes away. And then the bottom lower stack frames, right, they're just sitting in the waiting queue, waiting for our methods to complete. Right, so like global variables, like heap-based variables that are tracked by those lower stack frames will fall under same situation. Okay, so let's see. Let's go. Let's see. The question is, isn't this approach someone a waste? Both keep accessing memory. What should be the fast memory and spending resources and moving information between memory types? Right. So it's kind of think of it like distribution. Like Amazon has a bunch of distribution centers, right? It would be easier to keep one center in the middle of the United States that has every book that they're selling. Let's say they still sold physical books, which they do, of course, but that's not back when they first came along, that's what they did. It was just all about physical books. Then they moved to CDs, and then they are where they are today. If every order had to ship from one central warehouse, it's going to take a long time to get that book to anywhere other than somewhere very, very close to that warehouse. So if I got to ship a book to California, ship a book to New York, and it's in the middle, it's in the north of Texas, let's say, it has a long way to go. So instead, go ahead and we grab 1,000 books, and then we ship that 1,000 books off to a distribution center in Southern California, a distribution center in New Jersey, distribution center in Seattle, wherever. And then when someone wants a book, we can then make a shorter trip from those distribution centers. So it's the same, basic same idea, where that central distribution center is the RAM, and these sub distribution centers, which aren't as big as the main distribution center, they hold smaller sets of values, and they have to, as we consume the resources in those centers, we have to then ship more in, but then we ship 1,000 at a time, which is a lot more efficient than packaging up 1,000 orders and then going in their 1,000 more or less different directions. Yeah, so here with this one, let's see if I can get it. Let me do an annotation. That'll probably be easier. All right, we got our good old heap space. And we have our various allocations. We'll talk about the various allocation strategies later. But most often it's going to look like this, depending on what we're making. All right, and the first stack frame may have made a few. Let's get some other colors in here. Next stack frame made one. See how well yellow works. That one made a couple. Yeah, let me reverse the flow here. Let's say it was going like this. And link up a few things here. Just to track who made what when, more or less. Okay. All right, so say on stack frame 5, we decided to create a linked list, tree, whatever it is, and these are the objects that being dealt with on this particular stack frame. And then we do a traversal, we do find the smallest value, tree operation, tree operation, tree operation. All these objects in memory and there will be, for any application that is around for a little while, the heap's going to tend to grow in time with all the various objects that are coming and going, being created and tracked. Right, especially with our stack frames, right? The main stack frame, whatever it created, unless it passed a reference along to someone else, these two older items, they're less exciting. So we can't pull all of the heap space that was allocated to our application and into our caches on the CPU, but pulling in the various references that are in stack frame 5 into those caches might be something that we want to do. All right, let's see if I can kill the table here. There we are. Right, and not all the decisions are going to be perfect. Sometimes we might decide, oh, we needed a couple extra items, right? So when we decide we see that we're using this heap space quite often. When we grabbed it, we may have grabbed in such a way that we grabbed all 5 of these items. So we have a couple items that are actually in the cache that we really aren't getting any benefit from. Right, and that goes to our other part of spatial locality. Is with the sequential locality. It's also space-based, where we tend to operate on areas of memory, one after the other. Right? The primary situation arising from the von Neumann computer architecture, which is along the lines of fetch an instruction, execute, and fetch the next instruction. Instruction, if I can type. Let me see if I could get a link for that one. Right, you read your program instruction, execute it, read the next one, execute it. Right, it's commonplace where we do one after the other type thing. Right, another example. Arrays. Very often, iterating down. All right, which is a sequential operation. Right, not always the case. Right, a binary search, not going to be doing things in a sequential operation. We'll very often see arrays interacted with in a sequential order. So another place where we see these type of arrays are with files, which are very large arrays, such as a music file or a video file, where if we start watching a video, we tend to watch that video in the order that it is produced. And unless you're my kids and you're jumping forward and backwards and forward and backwards and backwards and forwards and, you know, just sucking down all the bandwidth. All right, so when we detect that we're in a sequential pattern, what systems will do is they look ahead. Let's look ahead, right? In the case of videos, streaming smooths out the video, right? We're not, you know, right, doing the data on the fly as we get it. As we get it, playback speed is of a fixed value, and we download ahead of time and buffer that data. Another place where I first saw this pattern a long time was Google Maps, right? If you do Google Maps, if you go really fast, right, you get blank spots. But if you're going slow enough, right, what Google does, if you do the dev toolbar, you can see the network calls that it's making as you, let me get the window small enough so you can see that. Right, as I scroll the screen, and the scroll bar is getting smaller here. Let me bring that up again. Network, right? As we scroll the screen, it's loading the pages and it's going through an algorithm and trying to see where we're going ahead and possibly loading. Right? So if I go, really slowly, I'm not going to see any blank space on the edges, right? Because it's gone ahead and loaded that data off the edge of the screen, right? Based on the user's interaction. Same thing if we're streaming something. We go to YouTube, right? Let's go to YouTube, stream buffering. All right, and let's see. Here's how you can fix the buffering or whatever that is. Whatever. We've all seen this before. If we go to our sort videos, you'll see there's a little progress bar at the bottom where it shows the video that's played, and then there's a gray bar that's advancing ahead of it because it's going ahead and anticipating that that is data that you're going to consume very shortly. So it's gone ahead and pulled that data ahead down based off sequential locality of reference. Right? But if you're not watching the video in order, or you're trying to jump to the middle, jump back, jump forward, that's when you get into the situation of you have to wait. You have to wait, okay, for the request to be received that now I want minute 5 instead of minute 2, or minute 20 instead of minute 3 as would have been expected. And then you have to wait so you don't get to leverage that locality of reference. Right, so that kind of streaming also applies to file streaming. So if the file is already locally read, and say you have an iStream and iStream file, and you say file into your whatever count variable, right? So you requested 4 bytes of data from the file, right? The disk and OS are not going to just read 4 bytes from the file. It's likely to read 4 kilobytes or 16 kilobytes, depending on the file system, of data from that file in anticipation of the code reading the next 4, 8, whatever, 16 bytes of data from that file. So the next read operations would be much faster than the first. Because even disks, go back to new egg, more components. All right, where's my disk? Hard drives. Okay, terabyte disk. All right, where's my buffer? Capacity. This is a solid state. The solid state may not be doing buffering as much as the old spinning style we're doing. Let's see. There we go, 18 terabytes. Can't have too much space, right? Cache, let's search one thing, right? So they got 520, pretty good cache size on the disk. So, right, reading from spinning disk, right? That's the slowest thing that happens in your computer system by orders of magnitude. Right? The disks have to spin, the arms have to move, and then the data has to be read. And you have to remember that in most systems, one application isn't the only one that wants disk I/O. Or I forget the task manager up here. Now, no one's hardly doing anything at the disk at the moment, but it's still right. 6 or 7 various applications want the disk, and they're separate applications. So the parts of the disk one are going to be entirely separate, which means the arms have to go back and forth if it's a physical disk, right? It's not a great example because it's a solid state disk at this point, but the same thing applies if, right, because I'm not too sure how many concurrent reads solid states can do at the moment, but whatever it is, it's going to be a fixed amount. There's only so many lanes of traffic that the disk is going to support, but it's going to want to leverage the same thing because the cache that's on the disk, again, should be substantially faster than the disk itself. Otherwise, there's no benefit in having that cache. All right, and that caching can also go further off the disk where it goes all the way to the RAM, where we even load part of that from the disk that was buffered there, from the disk cache into the RAM cache, so that when we do our next read operation from disk, it's even faster because the speed of RAM is substantially faster than the speed of disk. Of course, it's also still way slower than the CPU itself. Right, and that's again on the sequential locality of reference, anticipating that the disk is going to read the next chunk right after that. This is where having fragmentation can reduce your system performance, especially if you're on a spinning disk. Got a question. The question is, what about when a program produces information, does it go through fast memory? So does it have to go through fast memory types before going through slower memory types? So it depends on which operation we're talking about. If we're writing to disk, unless we have the file open in read and write mode, it's going to bypass the cache because there's no expectation that we're going to be reading what we're writing because we just wrote it. So we should already know what we wrote as a general principle. But if we're talking about like I, we're doing I++, right? So we keep incrementing I. And that's where things can get even a little bit more trickier or interesting because we can keep incrementing I and we're doing that purely within the register. So we're going even beyond the cache. We're just sticking within registers. Right, because let's see. Just grab the first one. I guess it's good enough. Right, registers, which are even much fewer. I guess I have to sign in, or I should refresh the page. Okay, good enough. Right, the register space, which was even much less space compared to all the other caches. Right, CPU, arithmetic, logic unit. I don't know what the CU is in too long. That's probably the interrupts, program counter, whatever. You'll likely take this class as a junior, but registers, number of registers, very finite. Right, this would be a particular core. If we can get I all the way into a register, right, that's the fastest thing can happen. You do an increment command. It's an instruction that would be fed to the LU. It takes the value and increments it right there in the register. So it's very possible our copy of I that's in the register is at 2000 right now, and the value that we have in RAM isn't even that at that point in time. So because it's going to take time to propagate that update back to where we're storing it in RAM, which is going to take a lot more time than what we're doing here. So what it'll do it as like a periodic basis, like every 1,000 or 2,000 updates or on some sort of timing frequency, so many clock cycles, you can push the data back out. And that is the other edge of the sword, because I mentioned earlier, it's a double-edged sword. The other edge of the sword is that you can have inconsistent data, which is a problem we're dealing with at my company, where we have the system change the value, but the users of that value didn't get notified. Right? It's basically like you mail out Christmas cards to 1,000 people, and then 50 of them come back as saying, this doesn't work anymore because the information that you had about where they lived changed. and that operation didn't quite work as it was intended because you're operating off cache information, right? Someone's address that they told you at some point in time is cached because it's data that's not going to change very often, but people are moving all the time. So people's addresses change. And if everyone that is aware of the address doesn't get the appropriate notification, you have a stale cache and things can fall down and fall down pretty hard at that point. I don't know if I've said that enough in this course yet or not. Number one rule of data is you do not trust the data. There's all kinds of ways that the data is going to be wrong. The data may not exist, right? Like you have a configuration file, you're expecting it to have like the database name or something like that, or how many threads to run or whatever it is. No reference exception is going to be a problem for a long time until languages phase it out. I know .NET's been trying to phase it out. I think C++ has something for it as well. I forget, but so the data may not be there. The data may be wrong, right? We might be operating off a cached version of that. And this is where various attacks can happen. So like you go to a website and you don't log out. You go to your bank account, you transfer some money and you don't bother to log out. If you don't log out, the server that's tracking your session probably still has all that information in memory. And like something comes to the computer, they go back into the history, like, you didn't log out. I can go ahead and continue to transfer information, right? Two reasons why you should, of course, be using a public computer to do your banking. And secondly, you should make sure you log out as soon as you're done so that no one can go ahead and just grab that session that's stored on that computer and then go ahead and be you. And that session ID is basically worth as much as your password at that point. So make sure you log out of your computer system, your banking website when you're done doing those things. And there are, of course, attacks on systems where you open up a phishing email and you don't have to do anything and they manage to scrape things out of the operating system or from the browser and they find your details and they start trying to hijack your sessions and all that good stuff. Okay, so I want to keep things as close as possible because it's easier to get to them that way. And the same idea is just like when you go shopping, right? And so you drink soda. Do you buy one can of soda when you have 5 cans of soda a day on average? Or do you buy, go to Costco and get 35 cans of soda? So you're good for a week. Because it's more efficient to grab a lot of the item and then iterate through that lot than it is to just go to the store every morning, right? Some things we do that pattern. A lot of people go to Starbucks and they do it every day because you can't just go to Starbucks and get 7 cups and then drink cup 2 tomorrow and cup 3 the day after that, all that fun stuff, because that particular system isn't well designed for that scenario. Right? You'd have to go alternate methods, buy a bag and then grind it and brew it yourself locally. But computer systems and physical systems can share a lot of similarities in this, where we develop the system in such a way to try to optimize on the behavior of the data in that system, where the soda or the coffee is the data that we're operating on, and we want to make things a little more efficient because we don't have to drive to the store or the Carl's or Jack in the Box or wherever it is you get your soda from every 3 hours or once a day or twice a week, whatever the frequency is that is you're consuming that given data for. Let's see. Yes. All right, pipelining. And let's see. I'm grabbing links. All right. That's probably good. Geeks for Geeks, let's pop it up again. All right, so for pipelining, All right, some instructions in the CPU take more than one clock cycle to work through their respective operations. All right, so this is definitely an area, again, here, anything that's CPU architecture, you don't need to understand the details of the architecture. It's just, this is an area of application for locality reference. So the instruction can go from state 0 to state 1, state 2, and be using different parts of the CPU to get this work done. This leaves parts of the CPU available for work. So what pipelining does is fix there, is make use of the idle time and the other parts of the CPU by starting to execute the next instruction. Some of the time, we'll manage to already be partway through that next execution after we complete the first instruction and gain that time advantage. In the worst case, the next instruction wasn't actually the instruction we needed to do next, or it depends upon the result of the first instruction, and we can't proceed. In which case, we throw away the work, or we're just blocked. In either case, no worse off than we would be if we hadn't used the pipeline. Right, in a similar strategy at a higher scale, multi-threading is used in a similar fashion where we have situations where the thread be blocked, waiting for something, thus not making use of the CPU. We can get another thread up and running to make use of the CPU time slice that we've been allocated. All right, things like reading from disk, from socket are very likely to be blocking operations. Waiting for user input. And when, let me get the task manager back up here again, right? However many whatever's running. Let's see. All right, so zoom It's very, very busy. I don't know how many times it shows my mouse moving, right? The screen moving to you as it does to me, but it's one of many different things that all wants to make use of the various cores on the system. Right? With there being multiple cores, it's a lot easier to swap back and forth between the different applications because each application can just use a separate core. Yeah, there's a fair amount of RAM on here. You see, I often do a good job using it. My computer didn't update, so I only have Visual Studio running right now. Usually that's using up a few gigs. Yeah, a lot of my tabs are gone as well. But yeah, it's supposed to be 32 gigs, but about 216 gig sticks, and it was a couple months before I got around to actually building the machine. One of them didn't work. You know, RAM has like a 10-day return policy, whatever it is. So I bought, and you can't buy them by themselves. They have to come as pairs. So I got another 216 gig sticks. So now 48. That's the unusual number. Oh, perfect. There's my L1 cache, 768 kilobytes. All right, so L1 cache is going to be much, much faster than the L2, then the L3, and then that 48 gigs of RAM that you noticed. Right, and then I've got disk 1 solid state versus disk 0, and disk 2 both solid state drives versus my big disk, my regular hard disk, whatever terabytes that one is, which is much slower. So the operating system, the program files, things like that, where I want to load up the applications. If I want my applications to load up fast, they have to be read from disk and into RAM. So if it's a slow disk, like the regular spinning disk is, it's going to take longer to load up. If it's on a fast disk, it's going to load faster. So this disk is good for things that are, like if I have media or pictures or things like that, where I don't need to read those for the application to launch. I just need the application to go fetch those and load up. So if you're storing movies, right, it's just that initial, how long does it start to play the movie? And then from there, it doesn't matter anymore because it's just going to buffer the next 10, 20, 2 minutes, whatever, seconds, however many it may be, unless I want to skip around in the application. You can see, right, there are 7,000 threads and there's only whatever, 8 cores. How many cores are there? I'll be showing a different screen. There we are, 16, 8 physical cores, 16 logical cores, right? And there's still a whole bunch of threads fighting for them. These threads are coming from our various applications. But most threads are, of course, sleeping. But when they aren't sleeping, if I have a thread that's doing something, right, all of a sudden, right, Google Drive decided to go ahead and stop bouncing around here. Google Drive decided to start wherever it went, whatever. Steam decided to do an update and it wants to download something. So it's going to be blocking and waiting for information coming from the internet socket, and it's going to possibly blocking writing to the disk. But the CPU has very little actual work to be done. There's like, okay, get consume data from the socket, go back to the socket, get more data, and then tell the disk to write. And it's got little work to really do, so it's getting blocked. So what that thread can do is it can go ahead and yield its time because the time is split up and then shared amongst all the threads that actually want to do something, and they just bounce back and forth, right? So I've got more than probably 16 things trying to logically occur at the same time. So the appearance of multiple things happening at the same time is a little bit of illusion. With multiple cores, it's actually a reality now, but before we had multiple cores, we just had a single CPU, which you would still have on, smaller devices, older smartphones, or other smaller devices, MP3 players, things like that. It has to juggle. So, and juggling is a little bit expensive, but if you're not doing anything with the CPU, that's wasteful. Right. So there is a cost. So threads, again, like these other locality references, there's a double-edged sword going here, because if you're reading data that you don't end up using, you just wasted the energy that it took to get that. Or if you're trying to do things too often, if you have a bunch of threads that keep trying to bounce back and forth, back and forth, back and forth, when you could have done it without a thread, then you're creating more work than there was in an alternative design, and you're not actually getting the work done ahead of time, right? So, in your programming classes, sometimes you'll get into mutex, semaphores, a lot of fun, various fun threading terminology. But it's very common that you don't get into it very well. Threading is something you want to investigate on your own. Multi-threaded programming. Let's see if we can find a good article to point you at. Parallelism, yeah. All right, dialogues, talking about various things. Let's get some other links to it. It's probably good enough of a primer to get you some keywords to further dig on. But most of the time, you're leveraging threaded application development, and you're not having to worry about it too much yourself to write the threaded code. For example, like ASP.NET, ASP.NET IIS, and the .NET framework handles the threading for you if you have 50 people actively on your website and it's hosted on one machine, right? Everyone's, they're clicking the like button, they're writing their blog entry, whatever it is that your application does, it handles most of that for you, so you don't have to worry about it. But the threading is incredibly important because if someone decides to upload, right, their 40 megabyte video on a slow connection, and we only had one thread on your website to manage that, and you had 49 other people trying to do stuff, waiting for that to happen is very, very bad design. So the thread is going to step in there and take care of that. It's definitely something you want to read about. Threading's not on the test for how threading works and have fun stuff, because that's a programming concept, not an algorithms construct, but it's a locality reference area of application that is pretty much used everywhere. As we saw here, back going and looking at the processor, right? 7,000 threads humming through the system at the moment. Let's see. Okay. All right. Take a second here. I'm trying to remember what is up next. Any other questions at the moment? I just remember forgot to talk about deleting, resizing Hashtable. So let me spin back to that. Did we talk about that? I don't think we did we? I knew I was forgetting something. So I do like to forget more often than I care to. So please feel free to ask questions, especially if you think I forgot something, because all likelihood that I very much likely forgot things. I don't like to. I happen to do that too often. I think I only mentioned table resizing. Okay, hash table. Meeting and resizing. The big problem is, you talk about something so often, you kind of forget when you talked about it. Okay, so first off, deleting. Is authentication we're referring to? OAuth, which is open authentication. That's, I don't remember the internals of how that works, but that's just a Oh, what's the word for it? Industry standard, something, not the word I'm looking for it, but a way of doing the authentication, because you have authentication and authorization concepts. Authenticating is determining that you are you, and then authorization is that you have access to what you're trying to do. Right, so we can authenticate Bob as a user of bank A and has access to account 1. So he has authenticated and authorized access to account 1, but account 2 belongs to Tina, and neither of them is authenticated to use the other account because they haven't set up such permissions. Open authentication is just a security mechanism for doing that communication. It's not. I don't know if he uses hashing or not. I have, you know, the reading I've done on that was a long time ago and certainly not very deep. All right, so deleting from hash tables. Cannot simply remove the record, as that might cause lookups to fail. To fail. So we have a couple options. Lazy approach is to use a dirty bit, not a diary bit, a dirty bit that flags the element as having been previously occupied. If new data is likely to come along soon, then that hole might just become filled back up anyways. All right, so dirty flag example get. There's various ways we might implement it. We'll just go ahead and use a sentinel value. All right, so let's say -1 is our empty. Indicates empty state. All right, as data values come along, and let's get those here. Data and index, say we have 10 goes to 4, 20 goes to 4. And it's actually, how did that go? 3, then we'll have 30, go to 4, and then we'll have 40, go to 3. All right, so 10. First value, no collision, 20 comes along, no collision. And then 30 comes along and we collide. So just using linear probing as our resolution strategy goes down, and 40 comes along and it collides. All right, next thing we happen to do is a delete of 30. And before we get there, let's make sure we're doing how we're doing a lookup. So lookup, my lookup of 10 takes us to index 4, no resolution. Lookup of 20 takes us to 3, no collision resolution. Lookup of 30, 30 goes to 4, which then goes to 5 before we find who we're looking for. And then lookup of 40. All right, goes to 3, to 4, to 5. Get my arrow going there. And eventually to 6 before finding who we're looking for. So if we go ahead and delete 30, new state here. All right, 30 is deleted. We mark it as available with just -1. do these two lookups here. So try to do a lookup of 30. Right, 30 goes to 4, and then 5, and then right, we stop, not found. And then we try to look for 40, we get the same problem. We go to 5, 5 says it's empty. So we have stop not found, which in the first one, this is correct. And in our second one, this is incorrect because the data is actually in there. So instead of deleting it and setting it to -1, we set some other flag value, -2. So when we do our lookup of 40, we get to 5. Okay, where is this extra? Oops. Get to 5. We see that it is marked as dirty and we don't stop. And then we go to 6 and then find the data that we're looking for. All right, so the problem with this approach is that the lookup took longer than it could have. And we had to look at 5 when we could have looked one fewer time, or one time fewer. And since optimizing on lookups is our preferred approach, well, let's take a look at it a different way. So alternatively, we can collapse collision chain or possibly chains such that the lookup is faster. It can get a little bit tricky, especially when the chains run into each other as they have here. Right, so we have 30 and 40 are out of place values. Right, and the chains are what we saw here. Right. The chains to get to these are right 4 to 5 for 30, and then 3, 4, 5, 6 for 40. So when we deleted the value, instead of using a flag, we'll do some collapsing. And this one is fine because we deleted this particular value, which was fighting with the other chain, right? Because we had 30, which belonged to set 4, and 40, which belonged to set 3, right? They're crossing over their, right? The streams are more or less crossed over, which can complicate things. But in this case, not very complicated. We just shift the delete down in our collision chain, which no longer includes 5 in the lookup. So we have a nice shorter lookup pattern here. Things are still a little bit out of place. Right, and that's why, right, chaining is called chaining, because the collision chains just live in their own lists. So deleting from a chaining solution is much easier to collapse because it's a linked list. You just go in that list and then you pull that node out of the list and you bridge the gap. But when we're doing the open addressing schemes, the deleting becomes more complicated and we have to resolve it in one of these ways. Whereas chaining, not much to do there. All right. If there's a lot of crossover in the chains, we have to be a little bit more selective on who's moving. Right, the easiest approach is to take the last value in the chain and swap it into the deleted location. This way we don't break other chains by having the delete in the middle of those chains. Right, because if I had values that are going beyond, right, so I was deleting from chain 4, if I had another value that was in chain 3, down here index 7, and I just moved a value from chain 4 over, then I would have broken chain 3. How are we doing at the moment? All right. Okay. So resizing. All right. Since the table size component of where things end up, the normalization, having to resize table means building a whole new table as the buckets, aka index, where the values reside, will likely change. All right, so this, look at our code. Hashing, and I think it's in more hashing. Find it in a second here. I think it's in this one, is it? Should be the zip. Oh, it's so annoying when you have to wait for things to get out of the way. Let's get that down here. Yeah, it's not the exercise. Okay. Just extracting the code a time or two again. Must have unchecked my checkbox, not showing me the code. All right. This zip is a .NET example. I'm just using .NET so I can show you the internals of their dictionary. Waiting, waiting, waiting. Always fun to wait for the computer. All right. All right, just gonna add some random value to our table. So not that much matters, it's just a hash table. It's a key value pair. We've just been doing the hash map equivalents. We're just cared about the key because we don't care about the actual values that goes along with it. Key is driving the data structure and the logic. Go ahead and add a watch so we can see what's happening inside this little data structure. Eventually I'll get There, key collection. There's my buckets. Okay. So at the moment, we have 3 buckets to track all of the data that's inside. As we add more values, those buckets are going to get populated somewhere. So it looks like, okay, the first value happened to go into index 0. The next value, add it to a table. It's going to go somewhere, counts, keeping track of things. And it happened to go to index 2, right? As we might expect, it's going to be, I'm using random data. Not that it needs to be random data, but where we drop our values into the table, going to be somewhat random. If I recall correctly, I think the load factor .NET's using is 0.72. Yeah, 0.72. Once we try to cross this threshold, so it's saying 28% of empty table space is what we're looking for to keep our close to constant time complexity. So right now our table is 67% full. So our next add is going to cause our table to be resized. So we're going to go from 3 and it's going to have to make things bigger. And now we're up to 7. And a new value is now at index 0 before. No, it happened to be the same value. Go to random data. Let's see who's at index 2 at the moment. Now, aren't those thin odds? End up being the same location. Let's go ahead and add a few more data points so we can make sure it's not in the same location. When we get to our next resize, do this a few more times. Probably have to get to 6 out of 7 before we get our resize. All right. All right, we jumped to 17. And this time 0 is now an empty location. How about 2? 2 is also empty. There we go. All right, anything to note? I went from 3 to 7 to 17. We're using prime numbers. Not too sure where I think it doubles for a little while. It's just an internal heuristic to .NET's implementation of a hash table, where it doubles the prime, then goes to the next prime. I think it does it for a while, but trying to double every time, there gets to be a point where doubling is just too much. We can't go from 1 megabyte to 2 megabyte to 4 megabyte to 8 megabytes. That's just becoming a little bit ridiculous. We want it to grow in a way such that we can handle the next sequence of events with hopefully not having to grow again into near a time horizon. So each time we do this, new hash table, I never bothered paying attention to memory addresses to see what they're doing to that. After you create update the memory address or just swap out the references after it's done or whatever's going on, but it has to regrow. And it's definitely not a cheap process. Otherwise, not anything else interesting in this code. There's not much to it, just calling this add function. With .NET's implementation, right, if I try to add, oh, it was 32. Okay, I forgot that was, yeah, there's no, try to add the same value twice, it gets a little mad at you. Because just like with our binary search trees, 2 keys is guaranteed badness. Right? With our binary search tree, as a duplicate key meant we're going to have a dead branch somewhere. With our hash table, duplicate key means we're guaranteed to have a collision, and collisions are bad. Right? We're trying to avoid collisions, and the way that .NET supports that is by saying this is not supported at all. You can't have the same key twice. So if you need the same key twice, unfortunately, this is not going to be your data structure. You're going to have to find something else. I'm not even sure if they have one or not that allows duplicate keys, or you have to go ahead and build your own. All right, it's just like what we had with the binary search tree. If we wanted to allow for duplicate keys, there's a solution. We can just add a little chain off each node that says, here's all the duplicates and their associated values going along with it. You could try to uniqueify the key. The problem there is, how do you look it up now? Because say like the key is a username, user's not going to know when they registered the account. And you want to allow, because you integrated two different systems. You bought company B and they have their own set of usernames, and those usernames conflict with the set of usernames that we already have. So there's two ways to do that. You either have to force one of the two users to go change their name or change their name for them. Say your name's now Bob123 instead of just Bob, because there was already another Bob in the system. We just gave you another random number. And I think was it Battle.net that does that? Because I think in Battle.net you can see multiple people the same username, but they actually have a, there's a number behind it. That's not the username, but it is a username type thing that goes behind it, so that you can have your username and not have to do funkiness, but your account is bound to your email address. And that is guaranteed unique, because you can't have two people with the same email address, because email providers do it that way. But your question is quite on point, because this is how databases will do it. If you're using a primary key that isn't actually unique, they have something called a uniqueifier. Well, they will make it unique behind the scenes to force it. I don't remember that's for, is it for primary keys or is that for indexes? I forget. Yeah, right. All problems have solutions. It's just what you want the solution to be. Either one solution is saying no, and the other solution is we'll make it work. Right? There's just always going to be a cost with making it work beyond what the innate behavior is. All right, looks like a good place for us to take 5 minutes. Let's go ahead and we'll take a 5-minute break and then we'll come back. All right. Next up, garbage collection. This action is for collecting dynamically allocated memory in a memory managed programming language. Right? For example, like .NET, Java, some C++, if you include the library, and change your code base. Match. Right, so if you have C or standard C++, anything that you create on the heap, you're responsible for giving back to the heap once that allocation is no longer needed. Fail to do so, may have a memory leak. So I'm sure you're all familiar with Windows, especially older versions of Windows. I think they're all written in C++. I mean, the Unix kernel, it's written C++, right? And C++ is not a memory managed environment. So anytime there's a malloc, calloc, realloc, new, it needs to be corresponding free delete type thing that gives it back when we're done with it. But, programmers, even whoever you work for, are not perfect, and applications are so large, the likelihood of there being memory leaks is very, very probable, such that when you have dynamically allocated memory is no longer being used, but is still taking up space. There aren't any variables around anywhere that can reach to these allocations. So a garbage collector can be put into place to do the cleanup for you. So in those situations, programmer isn't tasked with doing the deallocation manually, but the collector will do it. It sees fit. All right, there are two common classes of collectors: reference counting and tracing. Tracing, also known as marking, is the more common of the two. At a collection interval, it will start from the defined roots variables and traverse those like a graph to see what variables are connected and which are not. Anything that is not reachable is garbage and can be cleaned up. Reference counting. Every time we have a reference variable on the left-hand side of an assignment operator, we'll go ahead and update the counts for that variable. The count goes to 0, then we'll immediately clean up memory. Update. Okay, so tricolor marking garbage collector. So this is a specific implementation of a garbage collector that we're going to go over. What we're going to do is we're going to divide the memory allocations. And again, these are, just view them as variables or objects into 3 distinct sets. Gray set, I do it wrong, gray set, black set, and white set. Sets. Initially, black set is empty. Gray set has the root objects, and the white set has all remaining objects. Okay, let's talk about roots. Root objects be local variables, global variables, stack counters, registers, whatever. All right, because some of the things we might also have in memory could just be code, which we've gone past and we don't need it anymore. The algorithm will repeatedly pull a value from the gray set, which probably just can be implemented as a queue, and blacken that object by pulling any objects that are in the white set that the object is a reference to. Reason why we do this is that items in the black set are not allowed to have references to items in the white set. All right, so consequently, gray set items may or may not have a reference to an object in the white set. Once the gray set is empty, anything that remains in the white set is trash. All right. So let's say we have some code. Int main. Yeah, let's do some global variables because we mentioned them. Global variables, of course, are bad. It's called tree start. tree, and let's start list. And inside main, tree equals build tree, which some sort of helper function that builds the tree. Same thing with list. Let's build list. Then we will have whatever graph, let's build graph. And let's get another tree. Let's go black tree, RB tree equals old RB tree. Good enough for now. So a garbage collection can happen at any time. Talk about the consequences of that later. But we're going to go ahead and say it's going to happen at this point. All right, so our roots that are relevant, we have our local variable graph. RB tree exists on the stack frame, but we actually haven't gotten to that. So depending on how our collector is implemented, it may or may not consider it to be a gray object. And we're going to do our collection there. So let's first see what our tree and list and all that fun stuff are. So let's just create some trees and lists. Arbitrary data. All right, here, good for our first tree. And just give them some labeling. Yeah, I guess might as well just have everything here. Yeah, let's go with box, keep things a little bit different. Our list linking through. And we'll see that's GH and I, more or less arbitrary values. Got our red black tree. Just another type of balanced tree. And we'll keep that a little bit smaller. Actually, we didn't get that far, did we? Let's see, where did we get? Pretty much wasn't built yet, so we need our graph. All right. Our graph, our array of linked lists. All right. Okay, let's not have it too big. Just go ahead and kill a bunch of these. And we got here JKLM. JK and L. I should put my labels over here as well. That's J, that's K. That's L and K. And K links to itself. Why not? Well, probably shouldn't do circular lists at this point. That's fine. We'll do it. And L goes to J. That is a funny looking J. Let's try that again. All right. black set, gray set, and white set. So initially, we have black is empty. Gray sets our roots. We have our global variables, tree, list, and our local variable graph. So we have tree, list, and graph. And then our white set would be everything else. We got A, B, C, D, our slew of alphabet soup here. J, K, L, and M. So go ahead and pull an object from the gray set. Gives us tree. All right, and tree refers to A. So we're going to go ahead and pull A from the white set. So before tree leaves the gray set, A is pulled from the white set. At this point, tree no longer has references to any objects in the white set, right? B, C, D, E, F, right? All these are part of the tree, but they're referred to by A. Right? Tree does not refer to any of the other nodes in the tree. They're indirectly referred to. So moving tree gets us tree out of the gray set. And I forgot to put my A up here. And into the black set. All right, so we'll just enqueue whatever we process next after it. And we'll keep on repeating. Pull list. List is going to go ahead and give us G. So we go ahead and update things. G will move. So we go dig G out of the white set from wherever it was and move it into gray. At this point, list can be moved out and add to the black set. The same reason as we had, right? List only had a reference to G. H and I are part of the list, but they're not referred to by our list variable. So we go ahead and confirm that tree does not have a reference to any of these objects, and list does not have a reference to any of these objects. All right, so we'll go ahead and keep processing. We'll pull the next item. Graph. Graph points to this list, which is its own name. So I'm just gonna say that's the graph list. I'll just add it here at the end because I didn't give it a proper name. All right, let's get our graph list back in there. So we can have something that we can see. That's the graph list, which is tracking this array, right? Our good old adjacency list. Pulling that out. From the white set. Means we can now move gray out, gray, graph out of gray. And the graph moves out. And the process will continue and rinse and repeat. Some of these times we will pull multiple values as we're about to with A. All right, we're going to process the next item. Rinse and repeat. Pull A. This is going to give us now three. B, C, and D that we're going to be pulling out of the white list. B, C, and D. All pulled out. Now at this point, A has no references to anything that remains in the white set. So it pulls out. And we're done processing it. All right, keep on working our way through, and eventually we'll get to whatever might be trash, if there is any trash at this point, with things being global variables. Then it's very, very hard to get rid of our trash. Right, and as this one stands, all of our objects are going to be reachable. G will get us H will get us I, J will get us K and M, and plus they're also here inside the list itself. So everything, pull, and eventually everything will be in the black set. There is no garbage at this point. So let's get this down into a trivial or a simpler pattern. Object references, or so just be a little more abstract here, so I don't have to worry about if it's a tree, it's a list, it's a graph, or whatever it is. All right, A is a reference to B and C, and then C as a reference to F, and then that'll be the end of it. Example 2 with trash to be found. All right, so black set, empty, gray set, which I need to tell you who the roots are. Roots are A, and that's that. Gray set's A, and then the white set, everything else. And forget about commas, just space. All right, so we'll get to the test. This is what the prompt looks like. Do tricolor garbage collection. Here's the roots. Here's the objects, and here's what they refer to. Right, do our state changes, which I'll collapse into one. A is going to move after getting B and C out of the white set. And we'll keep on processing. We'll get B out, and nothing leaves white on that transition. We'll get C out. That will bring F along for the ride. And then lastly, F leaves, and we're left with D and E as trash. D plus E are trash and can be reclaimed. How is this example working? Are we able to follow the transitions based off of this reference chart? This one's getting big enough. Let's do another tricolor. Let's do this as an exercise. All right, let's get a table. Data, references, and do multiple questions. Question 1 and 2, 3, and 4. Just using different roots. Very simple object naming, A, B, C, D, F, G, et cetera, et cetera. A refers to B, B refers to F. C has references to D and E. And then E has referenced H. All right, so what are trash if the roots are just A and C? What's trash if we have G and C as roots? And what's trash if we just have A as root? And that's good enough. All right, so let's take 5 minutes. Let's do 13 minutes. We'll do 8 minutes of trying to get this figured out, and then we'll go over it, and a 5-minute break in there as well. So we'll resume lecture at 10 after. Just go on mute. But if you have questions, just go and ping the audio, ping the chat for our answers. All right. So what's the garbage for the first question?
I got the garbage as being F and G.
Got F and G. Everyone agree, or do we have other? Well, if there's only one answer, in theory, that's the correct answer. We'll see in a moment. Click the wrong one. All right, looks like we need to trace this one out. Okay, so we start with A. A goes black when B goes gray. And we've got C. C goes black when D and E go gray. All right, so A's processed, C's processed. Go ahead and process B. B is reference to F. B's processed. Then we've got D. Nothing. E has H. And we've got that processed. F has nothing. H has nothing. All right, so that leaves with just D. All right, so if G and C are the roots, what are we saying? What are we saying the answer is? So we got to be wrong. Any answer is better than no answer. No such thing as negative points. G and C is our roots. What's the trash, if any? If nobody has any answers, I guess we'll just leave that one blank for now. How about ABF? All right, let's check it out. As we did before. All right, G is a root, C is a root. C and G, say we pull C out by getting D and E again. All right, that's processed. D gives us nothing, E gives us H. G is processed. G gives us nothing. H gives us nothing. So we get A, B, and F. And then just with A, right, A gives us B, B gives us F, F gives us nothing. So quite a bit of trash here, right? So everything that's not ABF. C, D, E, G, and H. No, shortcut's not there. A, B, F, C, D, E, G, H. All right. 5.4b, reference counting. All right, so here, see we have some code. Object star A equals new object Bob. We'll have references B, C as well, and Tom and Agatha. And we'll have object star D equals C. Object star E equals A. And then we're going to start clearing things out a bit here. A equals B equals C. And we'll track how our counts are doing. Let's see. And so here we want to make sure that we're nice and clear on the difference between an object and a reference to that object. Right, so Bob is our object. A is a pointer to wherever that object exists in memory. Right, so state and line. Yeah, let's see, let's put this as line number. Executed, if we can type it. So line 1 executed. And I guess put some line numbers in here. I'll make that easier to track. Our object is Bob. It has A as a reference. Its reference count is 1. 2 is executed. We've got Tom. It has a single reference. 3 is executed. We've got Agatha. And C is a reference. 4 is executed. And we're going to change the state for Agatha to now be C and D, referencing it. Line 5 is executed, right? So A is tracking Bob. So Bob's state's going to change from just A to A and E. Line 6 is executed. A equals B equals C, right? So C is tracking Agatha. So we're changing the state for Agatha, among others. So first we'll go ahead and do B. We have C is there already, D is there, and B is being brought over. When B is brought over, that means we're changing the state for Tom. Tom no longer has any references. That goes to 0, and we're going to immediately reclaim Tom, right? Because no one is tracking it anymore. And then A is also being overwritten. A was tracking Bob. That's going to go down because it's moving over to track Agatha. We've got 4 references to Agatha. Apparently they're our most popular object. And Bob goes down to just E. And so our post state, we have our 2 objects. And just complete that column. We have Agatha still sticking around, and we have Bob. All right, Tom has gone away. So we start adding more code here. If we were to say E equals any of the other letters, Agatha's being tracked by every single reference, then Bob would immediately go away. Let's do another one. More references, more objects. Typos and all kinds of good stuff. C equals B. A equals null. All right, after line 1, we've got Carla. A referring it. Object 2, we still have Carla with A and B referring to it. Line 3, Chris comes along with C tracking it. Line 4, C equals B. Right, so Carla is gaining a reference and Chris is reclaimed. Line 5, Carla loses a reference. All right, A goes away. We just have B and C. All right, so B and C would need to get reassociated with something else for Carla disappears, or final state, or just say current state of objects. Memory still just Carla. Questions about this one at the moment? Question, so once all the references to an object have been deleted, would there be a way to create a new reference to the object? No, the object is gone. So once it's gone, you'd have to create a new object. And if you have any state information from what that object was at the point in time before it was erased, it's gone. It's like you have a save file and you overwrite that save file with something else, it's gone. Or if you permanently delete a file from the operating system, it's considered to be gone, right? Assuming we're discounting any file recovery software, right? Skip the recycle bin and it's gone. It's not just marked as gone. It's gone as far as the system is concerned. And of course, that depending on the garbage collector, it could be done as a dirty delete where it sets that memory as available and the data is actually still there, which means we could, if we knew what the memory address was, go back there and try to reclaim it. But that would not be, from the programming language we're using, not programmatically accessible, but it's still there. So if we need to do these things in a secure way, we would want to mem set the data at that location in memory and then release the reference to it so that we don't have any credit card numbers, social security numbers, or anything, any MPPI data that is still floating around in the system memory that a memory scraper could then get a hold of. Yeah, it's gone. If we try to like Yeah, so the next time it's kind of like like the stack frame. When we complete a method call or function call, the old stack frame is still there. The data is still there until we go ahead and make the next call and we just overwrite the previous contents. That's the basic, really common memory operation that happens with the system. You say it's quote unquote deleted, just like with a file on the file system. If you delete a file in the file system, it just goes to the file table and says that file's just no longer an entry in the table, right? It doesn't bother with the effort of going to disk and like zeroing out all the bytes to actually wipe it clean. We just say it is clean. Trying to think of a physical way of, kind of like, right, throwing something in the trash can. Right? If I take a piece of paper and I throw it in the trash can, as far as I'm concerned, the piece of paper doesn't exist anymore. It still exists. It's buried in the system somewhere, underneath some bananas and leftovers or whatever else has come along after it, but it's not gone until, it's fully decomposed and back into the earth type thing. Doesn't sound FedRAMP complaint. What is a FedRAMP? Schrodinger's memory. Was Schrodinger's cat, where you don't know, right? Quantum physics, you don't know the state of the cat. Is it dead or alive? So it's both dead and alive. That's not quite our state here, where the data is there. We're simply, it's hidden behind the screen, so we don't see it anymore. It's because it's in the trash can and it's gone from memory, out of sight, out of mind type thing. Oh, HIPAA. Okay, yeah, sure. Yeah, there's all kinds of data rule systems for what you can and can't do with someone's data, and how you're supposed to properly handle such data. My company does payment processing, so there's all kinds of rules there for how long we can hold on to data that came from your credit card or debit card or whatever that may be. Let's see. Okay, let's create my numbering. You're correct. It's like I'm busy. Okay. Create some exercises for you to do later. Go over your answers in Discord or next time, whichever it is. All right. And the way we do the test question is on what line? What line is object? Bob, BBO, yeah, BBO. Yeah, might as well do it BB8. Reclaimed. All right, so we get our line numbering. Yeah, I'm not gonna bother the stars, or whatever. A equals BB8. Right, saying new object, all that fun stuff. We're just, yeah, we'll simplify it. We'll just say new. Right, pseudocode doesn't much matter. In talking about the code, the only programming language that I'm aware of that does reference counting is Objective-C. And we'll get to that in a moment here. You just figured it out? Okay. Talking about the pros and cons of the two of these. B equals A equals new D2, and then A equals new C3PO. C3PO. Is O and O or O 0? Yeah, I don't. Cool. And then A equals B, and B equals null. And we'll take the same code. Restart the numbering. Grab too much text and just rearrange. All right, same question, but moving things around, it's entirely possible that things don't get reclaimed. Turn back on. Let's see. Let's move that one over there. And equals that. And I'm just going to simplify syntax. If A didn't exist before, just by saying it equals something, it now exists. It's all same idea. Okay, so one versus the other. It's reference counting has a cost for each assignment. So the overhead is live as things are being altered. All right, so we have to maintain that reference count somewhere, and every time see an equal sign, we may have to update that table, right? Value type variables, that doesn't apply, right? If I say int x equals 4, the reference counter doesn't care. Int is just a value type variable. When the stack frame goes away, x goes away. If I say int star x equals new int, 12, now it's under the purview of the reference counter collector, and it has to keep track of things. Right, so there's never any trash. This system. So if we're an embedded platform where memory is tight, this may be a good approach. Right, and Apple is the primary. There might be others, but Apple and Objective-C, those are what they use for their I line of devices. So embedded devices are of course getting more and more powerful every year, and they have lots more space. But you got your smartphone, it's got like 64 megs of memory, right? It's still small. Maybe you got a 256 megabytes. It's still small. That's you're talking about static storage there, not dynamic storage for whatever its RAM is inside there, and whatever its RAM. I don't know how big RAM is on a smartphone. Okay, I'm curious. How much RAM on a smartphone? I don't even think it's gigs. Huh? It is 4 gigs. How about that? I was surprised it was that much. I was going to guess it was around 1. S7. I think that's what I have here. How small is it? 4 gigs. Okay, it's not too bad. Still, 4 gigs is quite a bit smaller than a lot of other systems. It's enough that we can actually have dynamic allocated memory. Some embedded systems are so small where you're relegated to C or assembly level instructions because the overhead of an entire object being allocated on the heap and heap management, all that stuff, that there's not enough room in the system. So all that is not happening for you. Our tracing family doesn't have that overhead. But can periodically get bogged down if there is a lot of trash. All right, typically it's going to be on its own thread. And that will also take resources and has the side effect of leaving trash around for longer than reference counting does. I'm sure there are a few other things that I'm spacing on at the moment, but those key things I've seen. .NET uses a tracing garbage collectors for its stuff, and seen systems where so much trash is being created so often that basically the garbage collector was taking a significant amount of the system resources because the code was so poorly written that it just kept making too much trash. You be careful with strings in languages where strings are immutable, as any string manipulation will likely lead to lots of strings being made and consequently becoming trash. Let's see. Time. All right. One last thing in garbage collection. Compaction. And we're going to be talking about compaction again later, but for now, as the garbage collector clears away trash, that will cause holes to become present in the heap. These holes are known as external fragmentation. Fragmentation reduces performance as we're unable to leverage locality of reference as well as we could if the data isn't all together. So what we can do is a compaction and move data around such that there aren't any holes. All right, so basic idea. So you have various objects like something along these lines that got created and then deleted over time. And that our memory looks something like this. Fragmented. Collapsing this would be to move things to fill those holes. And there's different ways that this might happen. We just shift everything, or we can find things to fill the holes. Now we are defragmented. Right, same sort of thing. In fact, do I have show it on this computer? Since I am an admin, if I can get the pop up. All right, is it going to pop up? There you are. Let's see what kind of fragmentation I have here. Nothing's fragmented at the moment, apparently. So I don't have anything to do. So to analyze, find out what things are fragmented, but files come and go, especially with the internet browsers, temporary internet files, they come and go all the time. And that can cause the disk to become fragmented. And the way the disk systems work, we'll talk about this more when we talk about memory allocation strategies and fragmentation in general. But a way the files are typically wrote, if I have a massive 4 GB file, that 4 GB file may not be in a contiguous chunk of disk. It might be a couple megabytes here, 10 megabytes there, and it's separated out. That means as if we were to, if I was a video or a media file, and I was running through it, as it got to the end of a particular chunk, the disk would have to move to a different location to get the next chunk of data. And that movement on non-solid state disks can be a little bit of a delay for things, because it has to do the seek, arms move, all that fun stuff. Solid state, it's not enough of an issue that you would want to do this. In fact, they don't recommend you defragment. In fact, you can see it doesn't even give me the option to analyze it, because the amount of I/O that defragmenting a system does on a disk is it can be quite extensive. And basically it's like, nope, you don't even want to analyze it. And I'm not even going to click the optimize button, because that's going to shorten the lifespan of my drives. And the last time I did do this, probably a long time ago, you give you two options. There's a fast mode, and then there's a slower mode. And unless you have a UPS on your machine, you want to use the slow mode, because what the fast mode does is actually reads the file into RAM to make that space available, and then it can write another file into that location. And then as space is available for that file that's in RAM, it can write it back to disk. So there are points in time where you have files loaded up in RAM only. So if you lose power, then you lose your files, because they've literally been overwritten by other files. Probably not something anyone's very likely to do on their personal computer at this point, but server platform systems that are doing a lot more file operations, files coming and going, especially with log files, writing log files, and server applications is a very common thing. And log files tend to get aged out after a month, 3 months, something like that, to free up space. So getting a fragmented disk over there is going to be more and more likely. So they'll have to periodically do that kind of server maintenance. But that's the idea, just pick things up, move them around so we can make larger ranges of the disk more accessible to our operations, which makes it easier to allocate memory because most of the time we just keep filling up, filling up, filling up until somebody comes along and says, that's trash and I don't need any more, and makes another hole. And so same thing, it can happen in RAM to do to the GC doing its job. Happens on your disk system as well. We'll swing back to this a little bit later. Talk about our memory allocation strategies and just fragmentation in general. Let's see. Okay, swing back to where we are in the labs. All right, so we have Matter Hashtable lab due in a couple days. Any questions on this particular item? If I recall correctly, we did look at the code foundation for this last time. It's just arrays, nothing very exciting there from a code perspective. I take silence to mean that I've put everyone to sleep already. So you have no questions at the moment? Okay, the practice test. Function, for the function hash int, we include variable with it, right? Yeah, the int is the variable because the variables are just integers for the lab. Yeah, the hash int, that's just a prototype. So remember prototypes in C++ do not need to have the names int, hash, int, and then you have int hash. Actual implementation. Right, that's prototypes don't require the names, only the actual implementation of it require the variable name in there. Right, so the variable name is whatever you happen to name it. See, practice test. Sorry, this wasn't available. I thought I had it showing when we briefly talked about it last time. Were there any questions at the moment for this right now? Yeah. So go ahead and fire questions on the Discord channel. Any questions between now and next time? And we will get those answered. Otherwise, the balance of tonight is just working on the hash lab and break time. So there's no additional lecture at this point. So let's start cranking on that hash lab and then fire your questions at me. And I'll keep floating around for the next hour. All right, good night. And don't forget the test is next week. Oh no, there's still more in the course. There's just nothing additional for tonight. And we still have what, 4 weeks? And the finals May 23rd. Yeah, a little bit over 4 weeks to go. All right, see you next week. Oh, here I am answering the question on mute. 25 questions on the next test.